Let's dive right into this explainer. Every single day, we're literally trusting our lives to the invisible mechanics of beams. We walk on them, we drive over them, and we work in skyscrapers that are entirely supported by them. But to truly understand structural integrity, we need to look way past the concrete and steel on the outside. But how do engineers actually know what's going on inside that solid steel? I mean, a beam's survival depends entirely on these invisible internal forces maintaining perfect equilibrium against whatever external loads are being thrown at it. When a massive load pushes down, the beam has to fight back. If it doesn't fight back perfectly, well, it fails. So how do we map out that internal battle? We measure this internal tug-of-war using two primary forces, shear forces and bending moments. Instead of getting bogged down in dense textbook definitions, let's just visualize it. Shear forces, they're basically like a giant pair of scissors trying to slice the beam right in half vertically. Bending moments, on the other hand, are more like grab a pencil in both hands and try to snap it by bending the ends up or down. Drawing shear force and bending moment diagrams is literally just the process of figuring out exactly how hard those scissors are slicing and how hard that pencil is being bent at every single millimeter along the length of the beam. To master this, here is our blueprint. We'll demystify these forces, look at beam supports, learn a foolproof 3-step analysis method, unlock some pretty sweet calculus cheat codes, tackle complex loads, and finally, predict deformed shapes.
So, step 1, demystifying forces and moments.
Before we even think about drawing a diagram, we've got to agree on a universal language for how things push and twist. For bending moments, if a force causes the beam to dip down in the middle, putting that lower section into tension, we call it sagging. And sagging is always a positive bending moment. Just think of it like a smile. Positive, right? On the flip side, if the moment forces the beam to arch upward, like a scared cat, putting the top into tension, that's hogging. That is a negative bending moment. Think of a frown. Seriously, just remembering the positive smile and negative frown is going to save you a massive headache later on. Moving on to step 2, types of beam supports. You see, before calculating internal forces, we have to establish the ground rules of how a beam is physically bolted down in the real world. Here's the key. Every single prevented movement at a support generates a corresponding reaction force or moment. If you've got a pinned support, it stops the beam from moving up, down, or sideways, but it lets it pivot. Because it stops movement in two directions, it creates two reaction forces, vertical and horizontal. A roller support, that's just a beam resting on a skateboard. It only stops vertical movement, so it only creates one vertical reaction force. But a fixed support is bolted solidly into a wall. It stops everything. No vertical, no horizontal, and absolutely no rotation. Because it stops all three, it generates vertical, horizontal, and moment reactions. All right, step 3, the 3-step analysis method. Now that we know our supports, let's lay out the foolproof framework for solving statically determinate beams. Step 1. Draw the free body diagram to outline every single applied load and support reaction. Step 2. Use the concept of equilibrium, meaning all forces and moments must perfectly cancel each other out to equal 0 to calculate the exact numbers for your reaction loads. And step 3. This is the magic trick. You virtually cut the beam. Imagine taking a highly precise X-ray and sliding it along the beam from left to right. By doing this, we map out the internal forces piece by piece. At every single millimeter, the internal shear and bending moments must perfectly balance the external forces on that specific segment. Connect the dots across all your cuts, and boom, you have your diagrams. Next up, part 4, the calculus cheat codes. Let's be honest, drawing dozens of virtual cuts and plotting complex diagrams by hand gets incredibly tedious. But calculus gives us a massive shortcut. These derivatives and integrals are literally engineering cheat codes. They let you instantly sense-check the shape of your diagrams without guessing. Get this, the slope of your shear force curve at any point is simply the negative of the distributed load above it. Even better, the slope of your bending moment curve is exactly equal to the shear force right at that spot. And if you want to know how much the bending moment changes between 2 points, just calculate the physical area under the shear force curve between those same 2 points. It's this beautifully elegant mathematical relationship directly linking physical loads to internal stresses. And out of all those math relationships, here is the absolute golden rule. When the shear force is equal to 0, the bending moment curve will be at a local minimum or maximum. If you are an engineer designing a beam, you absolutely have to know exactly where that beam is experiencing its peak bending stress so it doesn't snap, right? Thanks to this rule, you just scan your shear force diagram, find where the line crosses the 0 axis, and you immediately know exactly where your bending moment is maxing out. It's a total game changer. Which brings us to Section 5, Tackling Complex Beam Loading.
Simple point loads are easy enough, but real life is messy. Let's apply those cheat codes to a real boss battle scenario, a cantilever beam that features both a distributed force and a concentrated moment. Imagine you're mapping your beam left to right, and suddenly, wham, you hit a concentrated applied moment of 120 kilonewton meters. What happens? Well, it causes a sudden, dramatic drop in the bending moment diagram. It's a literal cliff edge on your graph. But here's the wild part. It drops the bending moment by exactly 120 kilonewton meters, but it doesn't affect the shear force diagram at all. The shear force just cruises right on past, completely undisturbed.
And what about distributed forces? Say you have a uniform load spread across several meters of a beam. Calculating the twisting moment from a big, wide, spread out load gets confusing pretty quickly. The fix is actually really simple. We just replace that uniformly distributed force with a single equivalent concentrated force right at the exact midpoint. If the load covers a distance of x, you just pretend all that weight is pushing down at a single point exactly at x divided by 2. It makes setting up your equilibrium equations an absolute breeze.
Finally, Section 6, Predicting the Deformed Shape.
We've done a ton of math, drawn a bunch of graphs, and talked about invisible internal forces. But now, let's bring it all back into physical reality to see how the beam actually bends under the weight of the world. This is the real aha moment. Even though shear and moment diagrams don't explicitly calculate the exact millimeter of displacement, mapping the positive, negative, and zero moments paints a flawless picture of the deformed shape. Wherever your bending moment diagram is positive, you know for sure the physical beam is sagging downwards. Where the diagram dives into the negative, you know the beam is hogging upwards over support. And right at the exact point where it crosses zero, the beam is perfectly straight for just a brief instant as it transitions from a sag to a hog. By just glancing at your finished diagram, you can literally sketch the exact physical curve of the stressed beam.
And that leaves us with one final, highly practical question. If you can use these diagrams to predict exactly where and how a beam will bend, if you know exactly where that maximum sagging tension and maximum hogging tension is going to hit, where would you place your structural reinforcements? It's the ultimate takeaway of this explainer. You wouldn't waste expensive steel reinforcing parts of the beam where the internal forces are zero. No, you'd place them exactly where your diagrams peak. By mastering shear force and bending moment diagrams, you aren't just doing math. You are gaining literal X-ray vision into the physical integrity of the structures all around us. Pretty amazing, right?